Cool. Okay, so let's start it. So today's presentation is by Xinyu Chen from postdoc at MIT, and he's going to talk about machine learning and optimization for understanding spatial temporal systems. Please.
Thank you everyone for joining us. It's my pleasure to visit UCF, and especially thanks for Professor Shai as AI initiative for this short talk. And today I want to introduce our recent research about time series imputation and time series periodicity quantification. The general framework is machine learning and optimization for understanding spatial temporal systems. In real-world systems, we can connect different kinds of spatial temporal data in different domains, just like transportation, mobility, climate, and other scenario. We can connect just the figure 1, which is traffic speed, traffic volume, collected from highway system, and we can collect the data by using Uber trajectory. And this kind of data can be summarized as the network traffic state. And especially in human mobility, we can detect the trajectory of each vehicle and even for each passenger around the city. So we can also have the summarized data as origin destination, just as can be summarized as a mobility network. For the climate system, you might be very familiar with that because we can see this is North America temperature data. You can see hot areas like in Florida and cold areas in Canada, as I was studying my PhD there. We can also see surface temperature data, but in all of this kind of data, we have spatial temporal setting. The difference is that how to categorize this kind of data with machine learning, how to find some knowledge or patterns from this kind of data by modeling the high dimensional setting, multi-dimensional setting, and other things. Because our system, like mobility network, and even for the climate system, they are time varying, they are changing over time. So how to detect the changing system behavior by using unsupervised machine learning? I will give some new ideas about that. In my past research, we hope to highlight our research contribution from both the methodological and the practical side. And for the practical side, we have a lot of spatial temporal problems. We reformulated the problem just like summarized as traffic imputation. We hope to impute missing data in that case because we have the data as summarized as matrices and the tensors. We have a lot of missing data. So how to impute with high accuracy? That's the most important thing. The second one, I hope to give some new ideas, just like mobility pattern. They might have a kind of regularity or pattern changing over time. So how to identify this kind of pattern with a certain machine learning model, just like tensor decomposition or dynamic mode decomposition. The last thing is seasonality, because we can represent our data as time series data, but this kind of time series data is quite unique because our climate system has a yearly cycle. If you consider the time series data as a monthly time resolution, you can see 12 refers to the yearly cycle. You can see very strong seasonality in North America, and you can compare patterns across different decades. We also hope to make some contribution from methodology itself, just as we develop a tensor decomposition model and the sparse autoregression with interpretable machine learning perspective. Another tangible research contribution we hope to highlight is reproducibility, because currently we can see a lot of publications, papers, and other things. But one thing is that how to make the last mile of our domain knowledge, just like AI for spatial temporal data computing. We have different topics. We can approach publicly available data, and we can approach a different baseline model. But the case that we have standardized the programming language. We have standardized the Python packages like NumPy and CoolPy for GPU and CPU, respectively. How to do that with a single framework as reproducibility? We hope to highlight our past work about reproducibility. In our research, the first project is machine learning for traffic data imputation. We provided a lot of data sets, and in the meanwhile, we gave some Python implementation with just simplified with NumPy and CoolPy for GPU. And we also hope to try to push some blog posts to help people understand. This is a kind of tutorial for people to understand what we have done about our research. So we have tensor decomposition for machine learning and a general framework as spatial temporal data computing. I would like to introduce first work we finished in 2022 with also with our collaborator, Professor Han Jin Cai here. and other collaborators like my supervisor, Nicolas Sonia and Li Jinsen in Canada. In that research, we hope to give a general framework as a time series imputation. We started from convolution, definition, and then we hope to connect convolution with a fast Fourier transform and even for L1 law minimization in that case. In transportation system, we can connect different kinds of data. Like this is the network here. We can connect the traffic volume data and traffic speed data. For the traffic volume data, we can see that data with a certain time resolution, just like 5 minutes. This can be represented as time series here. We can see quite a strong daily periodicity and the weekly periodicity. This would be the global pattern of the data time series data itself. Another thing is that as we have continuous monitoring in the system, and we have different spatial locations, and for the different time step, this can be summarized as a matrix structure. This matrix structure shows a very strong spatial temporal correlations. We can find the spatial temporal patterns in that kind of data. But the question is that if we have another missing data, how to impute the missing data, how to improve the quality of that kind of data? So we started from the basic idea as we have partially observed data. We have assumption that our data shows just like global pattern. Global pattern means daily periodicity, and local pattern means just like local consistency. They are very continuous in terms of time series data itself. We have two examples, traffic volume and traffic speed here. We have just 5% observations, but we can impute missing data here. In spatial temporal setting, if we have spatial dimension and temporal dimension simultaneously, just like here, we have 600 meters as a kind of real sigma. We can collect trajectories of different vehicles. This is about 20% trajectories in the highway network. By doing so, we can visualize this kind of heat map as traffic speed. The red color refers to the no traffic speed, and we can also see freeway traffic speed here. By doing so, how to utilize the spatial temporal autocorrelation in that case to improve the imputation, just like the completed one as our target. This can be summarized as a standardized machine learning problem. This is just the imputation in computer vision, but in our case, we have the setting for the missing data by using the trajectory of vehicles.
So this thing, what's the input is a video, you get the vehicles and you measure the speed and so on.
Yes, this data has been collected by videos. We have the trajectory of each vehicle, and then we can build the trajectory here as a speed field. If we have, we only have 20%. This is the incomplete one. Yeah.
So the trajectory is the like GPS coordinate at particular time of each vehicle or something.
Yes.
And who did that? Like I know about NGSIM data set, but who has generated actually trajectories? You got from NGSIM?
Yeah, we got this kind of data from NGSIM. They have been processed. This is a very classical data set. But currently, they also have some other data sets in the US, like I-24. And in Germany, they have ID data collected by using DJI. Yeah, this is a little different. Yeah, let's go back to our formulation. If we have time series like here, we have global patterns. A global pattern can be summarized as assumption on the time series itself, daily and weekly periodicity. For local ones, they must be continuous in a very short time period. So that kind of assumption can be formulated with machine learning. Let's go to the first idea. As we have time series data points from x1 to x5, we can build the naive connection. This connection is just a graph. This is an undirected and scalene graph. We can represent this graph by using algebraic structure. This is a Laplacian matrix. This Laplacian matrix is 5 times 5. This is a squared matrix. We can see that in that matrix, we have the same entry on the diagonal. This is a totally circular matrix. So it's possible to extract the first column to represent all the information in this Laplacian matrix. As here, we can say this is a Laplacian kernel, as we have the first column of Laplacian matrix as the whole information here. The motivation for doing that is what we want is we want to reformulate the temporal recognition in terms of circular convolution, because if we have the recognition term as a Laplacian matrix, and this is a vector, time series vector, this is a multiplication between matrix and vector. But sometimes if we have a very long time series, just 1 minute, it's impossible to build a very large Laplacian matrix just like 1 million times 1 million. I don't think computer can get such kind of memory. But in our case, if we have the first column represent the whole information, then we just need to save just one column with 1 million entries. So we have circular convolution here. This is totally equivalent because the Laplacian matrix is a circular matrix. So we can convert as the circular convolution between Laplacian convolution.
Like, so you start with the graph, right? So what's a graph of? And is that the matrix is adjacency matrix of graph or something? What is going on there? You have the 5 nodes, x1 to x5, yeah?
Yeah.
So what's the on the right side? What's the matrix? How do you get that?
Okay, I can explain more about that matrix. For every data point, we have for the degree S2. This is the connection with other data points, just like X2. We have two connection with X1 and X3. So we have the connection degree here S2. And for the connection itself, we have the connection between X1 and X2. So we can use -1 to represent the connection. This is adjacency matrix.
Graph adjacency matrix.
Yes, this is just the degree matrix minus adjacency matrix.
Okay.
So this would be the Laplacian matrix.
Okay.
Yeah.
But what is this graph? What does this graph represent?
Oh, this is a graph. This is a graph, just a graph on time series connected from X1 to X5.
Okay, so these are the time series, the entries themselves.
Yes, yes.
I'm trying to say is that let's say you have a weekly cycle, right? So Monday to Tuesday to Wednesday to Thursday, Friday, but all the way to Sunday, but Sunday circle back to Monday.
Sure.
Okay. Let's go to the next part. We already introduced the local chain modeling. We hope to connect the data points locally. And another thing is that how to build the global chain, just like seasonality here in our time series. So we started from time series from X1 to X5, then we hope to build a circular matrix. This circular matrix can build the correlation between rows and columns, and this could be meaningful if we have a matrix nuclear norm minimization or matrix decomposition here. One special case of convolution matrix is a circular matrix. Convolution matrix is a general definition for that kind of structure. There would be two types of model in literature. One is a circular matrix nuclear norm minimization. Another one is a convolution nuclear norm minimization. And for that case, we can take a look. If we have partially observed data as a vector y, then we can estimate the decision variable as the vector x. For the minimization on the circular matrix with nuclear norm, then it's possible to compress information as small as possible. And that kind of model is very efficient for global trend modeling. But if we consider we have both global trend and a local trend, we have two components in the objective function. So we use a circular matrix to characterize the global trend as a nuclear norm minimization. And for the local trend, we have temporal organization as we defined a Laplacian kernel here. That's a whole framework as we have a matrix here for characterize the correlation between rows and columns.
Yeah, so I think we can slow down, just get the intuition, right? So you have these 5 nodes,
Yes,
right? And what does each node represent? What is that?
just like traffic volume of current hour.
Okay, good.
Yeah.
So you have 5 hours or 5 days.
Yes,
The traffic volume at first day, second day, and so on.
yes.
So then you have a graph which represent how the volume is changing or something. Why do you need a graph? It would be pretty simple idea here.
Yeah. In most cases, we have a very long time series. But if we want to characterize local autocorrelation, we should use just like the connection between the nearby data points. But as we have time series just for 1 minute, then we will have complicated autocorrelation for the global trend. Just like we have hourly resolution, every week we have 168 data points. And for several weeks, we have very complicated correlation. Yeah.
No, but so you have very long, right, with the series.
Yes.
So then you're saying there's a local and global.
Yes.
Question is that the you why do you want, I mean, it seems pretty complicated. Maybe very interesting mathematically, right?
Yes.
But the problem you want to solve is given the traffic volume, particular day, you want to predict the next day.
Yeah, maybe we can go through the experiment if necessary. I will go through that for answer your
Yeah.
question. Yeah, let's go back to our optimization problem. In that problem, we have a decision variable as x. This is estimate of time series without missing data. Our partially observed data is the vector y. By using the objective function as here, we can impute the missing data with both global and local trends. And to solve this kind of optimization problem, we can convert the objective function here with the information of partially observed data. And we can give the linear constraint here by using ADMM. We can find a standardized optimization scheme for solving this kind of optimization. But one contribution we hope to highlight is what we build is about augmented Lagrangian function in ADMM. We have both circular matrix nuclear norm and the temporal organization as a global and the local one respectively. We have Lagrangian multipliers and the partially observed information. But one important information is that circular matrix nuclear norm can be converted as a L1 norm of fast Fourier transform variable. It's not so necessary to save a very large matrix as a circular matrix just by 1 million times 1 million matrix like here. Another thing is that we already mentioned we use Laplacian kernel to represent all information for local trends. So we can convert this one as a fast Fourier transformed variable with element-wise multiplication. By doing so, we can convert the original problem with circular matrix nuclear norm minimization as L1 norm minimization in complex space.
So can you give us a little bit of an understanding here? So first thing, like a computer scientist, okay?
Yes.
Computer scientists would immediately say that there is no reason to go into a matrix form from the graph form, because the graph form is algorithmically much simpler. You have blew up a small graph into a huge sparse matrix with a non-well-organized sparsity, right? It's not quite diagonal, you have stuff in places, right? So first, that's a super inefficient way to do it, right?
Yes.
And then after you do that super inefficient way, you are using fast Fourier transform to lower the super inefficient way such that you instead of taking advantage of the sparsity as it is, you are doing fast Fourier transform, which again, that it's going to work because you started with a system which was periodical to begin with. So the fast Fourier transform is going to be periodical.
Yeah.
Is that what is happening here? Because it's like one coming from computer science, you would have said, why don't you just compute on the graph?
Yeah, we started using graph. This is very naive because we have standardized autocorrelation as a -1 for the nearby data points. And it's not so enough, but in that case, if we utilize the simplified local chain with a fast Fourier transform, we can accelerate the optimization problem. We can adjust the autocorrelation just by a learning mechanism. It can be better. But in our case, we just want to provide an essential idea for the optimization problem. Maybe we can go next to experiment to see the results here to give an intuitive understanding. In that case, we have for Fourier transformed variable, we have for complex space for L1 norm minimization. So it's possible to find a closed form solution. This is a sharing cage. Just one concrete example is L1 norm minimization can be summarized as here, just a loop function with the right-hand side. And we have that closed form solution. This can be implemented by using fast Fourier transform. So this is in nonlinear time complexity would be very efficient for large scale problem. We are here just use some synthetic data of different lenses to evaluate the computational cost. This is empirical time complexity. We can see with the increase of data lenses, the computational cost is almost linear. This is not linear time complexity. Compared to the baseline model as a convolution nuclear norm minimization, because convolution convolution matrix Nicolino minimization cannot use the property of fast Fourier transform. We can see computational cost even as a linear time complexity, but the computational cost is so remarkable as our model is acceptable, almost linear. That's one advantage for our optimization by using fast Fourier transform. Another thing is that we hope to highlight our contribution in terms of time series, as we have 5% observation for the traffic volume here with 15 milli resolution. We have 3D data as here. If we only consider circular matrix nuclear norm, then the imputation is not so good as compared to the ground truth data as here as blue color. We have red color as the estimate. We have a lot of noises. But if we consider the local time series trends, just as a Laplacian kernel here, then we can improve the accuracy of that kind of imputation. We can see the red curve can match the ground truth data accurately. This kind of contribution can be highlighted by using that kind of figure. And we have additional local trend modeling with temporal organization using circular convolution. And we can improve the performance for time series imputation by using that example. Another thing is that we have to generalize this idea to spatial temporal setting as we have for spatial dimension, temporal dimension. This would be a kind of matrix. But considering that, circular matrix is not so helpful because it has connected in a circular structure. If we have the data without a periodic pattern, we should consider to use a flipping operator to convert the original matrix as another one as a flipping one. And this kind of flipping is just flip across rows and columns. And if we have original speed field as here, we can do flipping operator as this one. By working on this kind of speed field, we have partially observed data about 30%. We can impute the missing data by using global and local trend. This is the reconstruction by using our model as a LCR, Laplacian convolution representation. By comparing to the ground truth data as here, this was collected by using the whole trajectories for the speed field. We can see the high accuracy of this case. That's
what are you comparing against?
We compared against some matrix and tensor decomposition model in our paper as a baseline model.
Not like, what about you just say that nearest neighbor?
Yeah.
Do you beat nearest neighbor with this one?
Like
you are masking the trajectory for 70% of the vehicles, and I propose the algorithm which I can write in one line of Python code that whenever I don't know the vehicle speed, I'm gonna assume it's the same as the speed of the vehicle in the front and the vehicle in the back.
Yeah.
The average of those two. Can you beat that?
Yes.
You can beat it. Did you try it?
I'm not so sure.
Because I bet you that you can.
Yeah. I think I can, but it depends.
What exactly would justify what extra information are you taking into consideration? Because I propose to you that the long distance correlation does not exist, neither in space, neither in time. Like the speed of my vehicle here, once I know the vehicle in front of me and the vehicle behind me, it does not depend on the speed of any vehicle yesterday or things like that, right? Or is it? I mean, I'm just trying to understand why.
So is this related to diffusion maps? There's a
Yes.
diffusion map from this
Yes.
professor in Yale, right? Long time ago.
Yeah, I think so. Yeah, because this can be viewed as image implanting, but our scenario is very specific. We have trajectory data on this heat map, and for the images, they have missing data about the pixels. So we have the same task, but in our case, we hope to use the local information as very nearby data points would be very close for the pixel values, and for the data points far away, just like here, they have the end of row segment and the start of row segment. They also have dependencies.
Yeah, I think so. There's a lot of theoretical work here, math and good papers. So what you can try to do, because you have for 30 minutes left. Give an intuition, like application, where this is used. And as Dr. Bologna is asking, why is it good? Well, like you're comparing known methods, like the time series prediction, can you use LSTM? Like LSTM, the known model, right?
Yes.
Predict. So is it good compared to your convolution thing? What is-
Our model is used to learn from very sparse data. For LSTM, we should have a very long time series for training data, and there's a requirement for completed data. Yeah.
Oh.
It's a little different for the mechanism. And this is the first work. The second work would be time series periodicity qualification of the whole content. I'll answer your question of that. This is our ongoing research about quantifying periodicity of time series, just like human regularity can be summarized as weekly periodicity or daily periodicity. For the climate system, we have, if we have monthly time series, we can find the yearly periodicity from climate system. We hope to give a general idea as interpretable machine learning. And in that idea, we hope to reinforce interpretability by using sparsity. Sparsity can be represented as L1 norm and L0 norm. L0 norm is NP hard in mathematics, but it can be solved by using mixed integer programming, as we can convert the L0 norm as a linear constraint in the optimization problem. So we have two application scenarios. One is human mobility in New York City and Chicago. Another one is a climate system. We have collaboration with different people from different departments in that research. We can first take a look at our data. We can collect different kinds of human mobility data. They have different dimensions, like the data can be represented as a spatial location. Just as New York City, we have 265 areas across urban areas. And we can also collect the time series data with different variables, just corresponding to the different years. And we can see the time step if we have time series of every hour. In that case, we give two time series data. One time series data is passenger flow, and we can see morning peak hour and afternoon peak hour. By comparing data points with a weekly cycle, just compare yellow points here, we can see they are in the same trip quantity. And we can also see this one as another comparison for the periodicity in a weekly cycle. This is one example. Another example is this one. We collect some two data points like here, but there are a little difference for the data points. In our idea, we can categorize periodicity just by summarizing two dimensions. One dimension is x corresponding to the trip count at t minus k. Another dimension is trip count at t. If they are on the anti-diagonal, just y equals x. And then this means a strong similarity for data points with a certain gap. So we can check out the first time series here. We can see they are almost on the anti-diagonal. This means a very strong periodicity for the time series itself. If we switch to a daily cycle as 24, then there would be some outliers, also very close to the anti-diagonal. And it's also possible to compare between different time series, as we have for this one. It's very strong for the periodicity. But if we switch to another example here, and we can see this is not so concentrated on the anti-diagonal. The periodicity is less than the first time series. We started from this naive idea. We hope to give one concrete example, like here in the city of Chicago, we have two-way data. So if we pick up some data points like here, we can see the same trip counts for the time series data itself. How to quantify this kind of periodicity? Because they are very meaningful for our infrastructure, for the optimization, and even for the design of new transport modes. And
So in this one, the problem, can you go back?
yes,
So we have a data, you said, from Chicago, right?
yeah,
And so the time, different hours, our 24 hour, 48 hours, and so on. Then your trip count, what is the trip count means?
trip count means total trip count in a certain hour. We have hourly resolution. Just for example, if we have morning peak hour, just 8 a.m., then we can see the total trip count in the city of Chicago would be about 1.0 with quantity here.
So there's many,
Yes.
many trips people take.
Yeah, how many trips?
So this giving time series, so your idea is to detect the period in this, like.
Yes.
But
Yes.
why don't you just apply Fourier transform, give you a period, right?
Yeah. This is we hope to quantify the periodicity of a time series to see this.
So look, this is 128 hours is a week, right?
Yes,
Okay. So 128 hours, obviously a Monday morning traffic and the next week Monday morning traffic and the next week Monday morning traffic.
yeah,
And then you have the midnight, nothing, and then you have the weekends, and during the weekends is different, and so forth, and you have the stuff like that, okay? All right. We know this, right? This is like super well known. This is like the most well-known stuff, right? The morning traffic and stuff like that.
yeah. I agree with you, but
Yeah.
we started from this example to give more ideas about urban system because
What do you expect to learn?
okay, maybe let's go to the next part to see some examples with experiments. And we hope to introduce the autocorrelation between time trip count at time t as xt and xt minus k for another time step. The autocorrelation can be characterized by using wk if we have very sparse coefficients here, then we can identify the most important autocorrelation. Just as one example on this case, we can identify the weekly periodicity very strong. This is very obvious. But for other case, we might capture other information. In the secondary one would be the current hour, the next hour's autocorrelation very locally. This is k equals 1. And the combination as k equals 1 local and weekly cycles. And we proposed this kind of model by using the constraint as L0 norm because L0 norm can constrain the sparsity by using the number of non-zero entries. We have non-negativity because the periodicity is always the positive autocorrelated. So we have non-negativity for the constraint here. This can be solved by using subspace pursuit as a greedy method, but solution quality is not good. And another solution is by using mixed integer programming. We can introduce a mixed integer programming by using binary decision variable as upper bound for the parameter as the decision variable coefficient W. We have sparsity on the binary decision variable as a sparsity be a linear form. And here, if we have sparsity on this one for the sparse autocorrelation as sparsity equals 2, then we can identify two most important autocorrelation by using subspace pursuit. This is interpretable corresponding to a weekly periodicity, but k equals 53 is not interpretable. We don't know the meaning of that one. If we switch from subspace pursuit to mixed integer programming, then we can identify two most important ones as k equals 1. This is local autocorrelation. K equals weekly cycle would be weekly periodicity. We can also check out, we have the same constraint for the optimization problem, but objective function of mixed integer programming is smaller than subspace pursuit. This is more interpretable. I know in that case, we have strong periodicity because as identified here, this strength autocorrelation coefficient is very strong and stronger than the local one. But another thing is that as we have this kind of time series, this is related to GFK International Airport.
Before you jump over to the next application, what did you learn out of this? Because for instance, I can give you a couple of new stuff which I know from the system, that it's not only that you have this periodicity, you also have a symmetry which you kind of ignore, because otherwise everybody who takes the train to Chicago are going to get stuck there. So you know for sure that whomever took a train from the suburbs to Chicago are going to also take the train back, right? For instance, a lot of information. But what did you gain? So you pull split. What did you learn? What is the outcome of this?
Yeah, for that case, we can identify the weekly periodicity very strong. But another thing is that can we claim just using our eyes to say local autocorrelation is stronger than weekly periodicity, or weekly periodicity is stronger than local autocorrelation? It's very difficult. But using our model, we can identify.
Can you give me what does that mean?
The meaning is that
I was trying to figure here is just toy example to demonstrate the effectiveness of the model. Like potentially we want to apply to something we cannot easily understand, that we don't have that prior knowledge about, there's a weekly cycle where I mean, of course, for this particular traffic data, we know with so many parent knowledge, we know like that this kind of circle, daily circle and also weekly circle, probably there's yearly circle as well. But this kind of like the toy example to demonstrate the ability of the model here and the result meant to match to our common knowledge and potentially want to apply to something that we don't have knowledge about. For example, there potentially some ocean data, ocean circle, sorry, there are some like a long-term circle that is hard to catch by human automatically. Let's say the circle is like 2.7 year every time the circle every 3.7 year, right? So I mean,
So let's say that I don't know. Let's say that I don't know. I knew that there is something called I started with this data and I didn't knew about the fact that traffic is conditioned by the week and the day of the hour and stuff like that. Okay. Then you run this, whatever you are running, and something comes out. What comes out?
I
Is
see.
that W your output or what is the output? I'm trying to see what is the output.
The output here is the coefficient interpretable coefficient because we can find the
Coefficient of what?
coefficient of our time series because our time series would show autocorrelation at a weekly cycle. This autocorrelation can be characterized here as a kind of periodicity quantity. This quantity is 0.77. And this is very strong, I know, but in most cases, it's very difficult to find as strong as this one for the time series periodicity. Yeah, we just use this one as a top example.
W is
W is the autocorrelation here for the time series. As we have WK as the autocorrelation between XT and XT minus K.
This is the higher the W means for W is equals 128, it's the highest correlation between
Yes.
those hours.
Maybe we can go.
Highest correlation between those
Yeah.
set of time points. I think that's what.
is this a difficult problem? I'm sorry.
So as you mentioned, I think this is a toy problem, but in ocean cycles and environmental problems, if this algorithm will work, that because this is an obvious things to override that we have a cyclical pattern weekly in traffic, but other applications maybe you can speak more on.
Maybe we can go back to this figure because if we have trip count at t, this is xt as a y dimension. As we have another trip count at t minus k, if they are on the anti-diagonal, this means a very strong similarity for the data points, and this would be a strong periodicity in that case. And periodicity is just a kind of metrica for measuring our time series autocorrelation in a weekly cycle or in a daily cycle.
So one question is, why don't you use other techniques? For example, periodograms, Ramanujan transforms, which detect periodicity in data. Why aren't you using other methods?
Yeah.
What is the advantage that it
Okay.
brings about?
I think for the single time series, you can use everything, even including fast Fourier transform. But if we have a multi-dimensional setting, it's very difficult because yeah, I would like to say, and this is an example. You can imagine this. We have pickup trips and drop-out trips. Pickup trips is less seasonal because you can see pickup from airport to other places with a lot of noises in the time series itself. Every row correspond to the time series of each week. We can see the time series over the past 5 years. And this is drop-off. Drop-off to airport is very seasonal because this is very related to flight schedule. And by using our model, we can compute the coefficient vectors here. Just as a coefficient vector for drop-off, we have a coefficient as a weekly cycle and a daily cycle. And also for the pickup, we have that kind of information. But this is comparable for two different time series. As we can see, the coefficient of weekly periodicity for dropout trip is stronger than pickup trip. We can also compare, this is daily periodicity. This one is stronger than pickup trip. So this can be meaningful for the comparability among time series. And we started from that idea to a general framework as a multidimensional setting. if we have a univariate autoregression, we can set sparsity, we can find the periodicity by solving the optimization problem. We can also use other methods like a fast Fourier transform, like a Ward method for that kind of time series. But for the multidimensional setting, we have different spatial locations, we have different variables. How to make the coefficients comparable across different spatial location, across different variables. We have this kind of model as a multidimensional setting for the autoregression. We hope to identify the periodicity just like here. This is autocorrelation as a three-dimensional time series data. We have spatial location, year, the data of a different year, and even for the hourly time step. We have sparsity for the constraint because for the coefficient, we hope to have the same support set. Support set means index of non-zero entries. We have upper bound as beta. If we have the single beta, then we can constrain the sparsity for the coefficient across different spatial locations and the different variables. And that kind of constraint can be reinforced by using the sum of binary variable as the upper bound as tau. This could be sparsity. Another thing is that as we have this very large scale multi-dimensional sparse autoregression, we have a lot of decision variables. Sometimes as we handle sea surface temperature data and the North American temperature data, we have millions of decision variables. And this is a disaster for mixed integer programming. We have solved this kind of optimization problem by using mixed integer programming. One example here is a mensual system. As you mentioned, we can do something about periodicity, but how to compare periodicity across different spatial locations? This is inflow periodicity, just the inflow to the mensual system, and this is outflow. So what's the difference between two figures? As we have categories for different level of periodicity, we have red one as the strongest one, and we have blue one and other colors. And we have a kind of finding for this kind of periodicity. As we compare, just to pick up the end stations of this line, this is almost in red color for the inflow, but for outflow, this is in another color with a less periodicity. This means our commuting trip is very related for the inflow, but for outflow, it depends. Sometimes it's not so seasonal as that case. We can also compare the end stations here. For inflow, this is seasonal, but this is not seasonal for outflow. The time series periodicity across different time series can be comparable even for different variables as the inflow, outflow. And we hope to use our coefficient as a certain metric. But in that case, we can select the three levels of periodicity. As the lowest level would be here, we can see the data points are not so concentrated on the anti-diagonal. But for that case, we have stronger periodicity. We use the station 15 as an example. We visualize the data because we have data in 24 days. We can visualize in 3 weeks for time series. We have a little difference in the first day and a little difference in other days. That could be a kind of not so seasonal patterns for the time series. But if we select the station 14, this is very seasonal. As we visualize the time series data across 3 weeks, they have a strong overlap. This kind of overlap means periodicity across different weeks.
I mean, it's interesting to identify patterns, whatever you're looking at, as the general theme. I'm trying to figure out what do you use this for from a practical standpoint. For example, can you use this data to improve your driving experience, for example? You know, and for example, if you're going out to the airport on a particular day, which route you should take. Or if there's some inclement weather, how you change your route. Or if there's an accident on the highway, how you choose an alternate route.
Yeah.
Those are sort of practical problems where there is a pattern in the traffic, and then some event occurs, and then you need to figure out what to do in those circumstances. Those are like practical problems. I'm trying to see where you see the patterns you identify coming helpful in some practical problem you're trying to solve.
Yeah, I think in that case, periodicity means kind of predictability. If we have a very periodic time series, then it's very easy to predict for the future data points. But in that case, we can see most stations are very seasonal for the trip counts, but some of them are not. So for the training data of a certain machine learning model, if we use a lot of time series data with very seasonal pattern, then it's very difficult to improve accuracy of difficult to predict time series. Just like here, small fraction of them very difficult to predict. So we should do something about machine learning downstream task, just like classification, other things to improve accuracy of time series prediction. This might be meaningful. And we can go to the next page about the periodicity of New York City and Chicago. And we can compute the periodicity of each area in New York City. And we can see in downtown area like Manhattan, this is not so seasonal for the trip counts. And we can see for suburban areas, they are very seasonal. This is the data in 2019. But if we switch to 2020 due to COVID, we can see time series periodicity is smaller than the past year. And we can see recurring process as a periodicity quantity recovering accordingly. As 2022, we can see the periodicity as the same level before COVID. After just as a past year, 2024, for the periodicity, we can compute the difference between 2024 and 2019 by just by here. We can see the downtown area has been less seasonal for the periodicity, but for suburban areas, more seasonal. We can also see the case of Chicago, because Chicago also shows a less seasonal pattern for the trip counts in downtown area. We can see in suburban areas, they are quite seasonal. But due to COVID, we can see in 2020, the periodicity values have been reduced significantly. It has been recovered a lot, but it's not so good because in New York City, in the past year, we can see the total trip count recovered about 94%, but in Chicago, this is only about 76%. The recovering process is not so good, but the percentage of periodicity almost recovered. And we can see less seasonal patterns for the less seasonal trip counts for the downtown area in the city of Chicago, but for suburban areas, more seasonal for the trip counts. Another thing is,
that's a very nice example, right? So you have evaluated New York City and Chicago. So what's the conclusion, like common people? What does this say they want?
Yeah, I think the main finding is that New York City recovered almost 100%, but Chicago is only about 100% for the trip counts. This is a ride-sharing trip.
So people take Uber, ride sharing?
Yes.
And in New York City, what happens?
I think for the city of Chicago, not only for ride-sharing trip, but also for transit, this is only about 70% recovery.
70% recovery.
Yes. This means that the recovery is not so good, but the human regularity has recovered to the situation before COVID.
Nobody understands, right? So tell common person, what does this say? So people are waiting for Uber and so on. So what's the recovery means? Well, I don't know what's recovery. What's the meaning of this?
I think the meaning is the trip, the mobility pattern of our current stage has recovered to the period before COVID.
Before COVID? Oh,
Yes.
it's about
Yes.
COVID.
Yes.
So COVID, the traffic pattern was bad. There were not many people going out.
Yeah.
So is this like 2019 with COVID?
Yeah.
So then after the increases, but isn't that obvious? Like people know that after COVID, there was no traffic.
Yeah.
So what is the
Another result is that as we can see, the periodicity has recovered to the same level of 2019. It's difficult to claim the total trip count recovery because our situation has recovered to the common one.
okay.
Even for the trip count as 70%, it's very difficult to recover to 100%.
No, okay. So again, periodicity, how do you explain somebody on the street? What periodicity mean?
It's a little difficult because this is aggregated data. This is the number of trip counts in a certain area. This is not
Certain area
related to the,
town,
yeah.
They repeat, what does periodicity mean for that?
The periodicity means a group of people have regularity from one area to another area.
Can you give like a explanation, like hypothesis law, what exactly is happening here?
we have
But I have a hypothesis, but I'm curious what you have.
we want to use this kind of model to identify periodicity and see the periodicity value to as a kind of special patterns. A kind of special pattern like here, downtown area is less seasonal. For suburban areas, they are more seasonal for the trip counts.
Right, but you know why this happened, right?
Yeah.
What happens is that when the companies said that work from home is over,
Yes.
right, periodicity goes back to where it was because
Yeah.
everybody who had to come back to the offices are coming at 9 o'clock and they're leaving at 5. That's why you have periodicity. The work from home in 2020, that's when you didn't have periodicity. And the Chicago New York difference is because in New York all the office space is again open, and in Chicago you have massive, and you would do San Francisco is the same thing, like you have massive buildings in downtown empty, and so because those buildings are empty and they are not used, you are not going to have trips because things like that. But is this a useful information? So like what is your contribution to this? Is this your data or you found this information? I'm trying to understand.
This is public valuable data. Our contribution is developing this kind of model as interpretable machine learning, starting from sparse autoregression. And we can compare our periodicity value learned from data across different spatial areas across different years. This comparability can help us summarize the conclusion as the recovering percentage of.
In this slide, what was your?
I think in this slide, our contribution is finding the result as periodicity has been disrupted due to COVID and then recovered accordingly.
So you took the data, you find the periodicity.
Yes, with our current model.
And your method is better than any other method to find the periodicity from the data.
Yes.
And it's fast also.
Our contribution is for the methodology. We have this kind of framework to identify periodicity from multidimensional time series. Yeah.
And so it's a theoretically sound and using some optimization.
Yeah, the optimization problem here is that we have millions of decision variables. It's difficult to compute with a certain solver like C+ or Groupie, but we have the essential idea by learning global support set first and then estimate using quadratic programming. This can be very efficient as we have millions of decision variable. We can compute just in 1 minute. Yeah, this is our contribution.
So I mean, if you look at AI today, right? We used to use quadratic programming, mixed integer programming. Actually, even this diffusion map I mentioned in the old days in computer vision, because we also have video, the time series.
Yes.
But now this deep learning tells us we don't need all that, and it just use gradient descent.
Yes.
And like large language models predict the next one, right?
Yes.
It's a huge amount of data. So this philosophical question.
Yeah, I agree.
Need all that. Why can't you just use transformer to predict? And will that work, you think, for your problem?
I agree with you. In that time series data, we used one example by using greedy method. Greedy method, just like subspace pursuit, we use the alternative minimization with the first step, maximize the gradient, the absolute value of gradient, and then estimate the least square solution. But solution quality is not so good. It's difficult to interpret, just as k equals 53 is not interpretable. If we switch to mixed integer programming, then solution quality can be improved. And that kind of improved solution quality is more interpretable. So we are trying to use mixed integer programming for exact solution of that problem. And we don't want to have misleading information for periodicity value by using gradient-based method, like a subspace pursuit. Yeah. Let's go to the next part, understanding climate system. As we have a multi-dimensional setting for the climate system, we have latitude, longitude, and the data of different decade. we have monthly time step for the time series data. So we can set up a kind of optimization with a multi-dimensional autoregression. We use the constraint as a sparsity constraint with upper bound as a single integer. By doing so, we can identify the periodicity of sea surface temperature data as a red color correspond to very seasonal spatial locations. We can identify for 4 decades. We can see the area of in the center of Pacific. This is a El Nino phenomenon area because the El Nino phenomenon is a special event in sea surface temperature. This will increase the temperature locally in the climate system. We can identify the spatial distribution of El Nino phenomenon here and here, just as a triangle. In another finding is that in that map, we have for seasonality quantity for different spatial locations. For example, we can take a look for Arctic Ocean. Arctic Ocean in the first decade is very seasonal, but in the second decade, we can see less seasonal. In the past decade, less seasonal. What happened? This might be a kind of dynamical system that changing over time, and we can use our model as a data-driven approach to identify the periodicity value here and verify what has changed over time. And we have discussed with people in climate science. They claim this kind of figure would be interpretable, just corresponding to some phenomena in climate system. And another example is North America temperature data. We can identify very seasonal time series in some areas like eastern of Canada and the US, and the north area of Canada, and even for some areas in the western area of the US. This kind of pattern for the first 2 decades are so consistent as we can compare. This is the minimum temperature, this is maximum temperature. They have almost similar patterns. But in the past 2 decades, they have changed significantly. As this one, we can see in this decade, this is so strong for periodicity across all locations in North America. But in that one, in the past decade, you can see the central area regions in North America is not seasonal. And this is Rocky Mountain. And this is north area of Canada. And this is Florida. And another thing is that we can say in the past 4 decades, Mexico is not so seasonal, even with a very small area. We can see they have green color and red color, very complicated. But in the past decade, for the maximum temperature, this is quite stable. This is a little different as a spatial pattern. That's all our finding in that research. Thank you.
So I have a quick question. So why do you model these time series as deterministic? Why not as stochastic time series in which people use things like variograms, so on, to understand spatial temporal correlations?
Yeah.
These are not deterministic.
Yes.
Series. And people also look at multidimensional time series in these cases. Is there a reason for this particular modeling approach? And maybe I can also add to this. People also use seasonal ARMA processes. For
Yes.
example, you can fit a model that has seasonality parameters instead of the autoregressive model that you have here. So why didn't you resort to these types of modeling techniques?
Okay, for the first question, I also used the Bayesian inference for building this kind of matrix or tensor model on time series. It can be used for uncertainty quantification with the basic assumption, just like Gaussian distribution. You can quantify the uncertainty of your estimate for your prediction or imputation. That's okay. And the concern is that if we don't care about the uncertainty, Bayesian inference is not so efficient, because if you use the basic optimization scheme as MCMC, you need thousands of iterations for your deep sampling. And this is not so efficient for large scale problem. And another thing is that if we don't care about the uncertainty, we can remove that. Even for the current model as a sparse autoregression, we can use another idea as a Bayesian variable selection. You can use a multinomial assumption on that model. This multinomial assumption correspond to L0 long minima, correspond to L0 long. You can use Z1 as an alternative. You can find the uncertainty of coefficient for the estimate. Yeah. It depends if you want to see the the uncertainty, you can use a probabilistic model instead of this one. This is deterministic with a certain optimization as mixed integer programming. You don't have possibility to see the uncertainty of your estimate. Oh,
Have you looked at other spatiotemporal domains for applications to this technique?
yeah, we also use the use the data in dynamical system as a fluid flow. You can see fluid flow has a very seasonal pattern for the for the data. You can see I don't know how to explain because dynamical system is a little different, but we have for one example in our blog post. Maybe we can take a look for that one. Go back. This is our blog post for introducing time series convolution and the sparse auto regression. We have for one example here for fluid flow. Let's go to that one. Yes, this one. In that figure, you can see time step 1 is consistent with time step 31. They are very consistent because this is seasonality of the fluid flow shape. It changes over time with a very significant periodicity. By using our current model, we can identify periodicity with that framework as t equals 30 as a periodicity value. Yeah, this would be a top example by using that case. Okay. I think this is a good question, but if we have optimization problem as here, we can use mixed integer programming to find the exact solution. Exact solution means that if you give your data, you can find the optimal solution. This is very robust. Another thing is that robustness would depend on your data set. Yeah, I'm not so sure, but you can try. Even for the climate system, you can approach very high resolution data because in North America, we use the 10-kilometer resolution. This is very large scale. If you use 1-kilometer resolution, it's very difficult to save that kind of data very large scale. But you can evaluate the pattern of using this kind of model. Yeah, might be consistent because I evaluated the time resolution of 5-kilometer, 10-kilometer, and 20-kilometer. They are very consistent for the seasonality pattern.
Chen, if I could go back to that slide on the aline and aline.
Which one?
The second, I think the last two slides there, map of.
Yes.
Now, are you saying that there is a change in the period of those 2 decades, or there is a change such that it doesn't look periodic anymore?
Yes. Yes. We can. This is very interesting. I don't know it's appropriate to say climate change or not, but there might be that kind of change for the climate system as we can see Arctic Ocean in first decade. This is very seasonal with a high periodicity, but in the past decade, you can see green areas. Green areas means less periodic for the time series here. I don't know what happened, but yeah, it might be a kind of change. And even for the North America data, you can see this decade is very seasonal, but this decade is not seasonal. Our model.
Go back to the previous one, and you say the seasonal features are less predictable.
Yes.
I'm trying to say, is that true?
Yes, it's true. Because for El Nino phenomena, this is less predictable. This is a common sense, as we know. Yeah. But for other areas with a very high periodicity, it's very easy to predict for the area like El Nino phenomena in the center of Pacific Ocean. It's very difficult.
So periodicity in this case, it's yearly.
Yes.
like the correlation between one July and the other July.
Yes, and the current May and the next May.
Have a delay, like the monsoon comes late, and then everything is shifted, and it's still seasonal, it's just that it shifted with a month, something. Is that
It depends on the setting of our model. Yeah. We have this kind of model, want to give a framework for finding some changes of dynamical system as in terms of transportation for human mobility and in terms of climate system. We can give some results like that using our model. They can be interpretable, but if we really want to explore what has changed over past 4 decades, we need to ask people in climate science. They would have intuitive understanding for the phenomena of climate system, like El Nino phenomena and other things. Yeah. And I also visualized the sea surface temperature in the past 4 decades. It has been increased about 0.39 degrees in the past 40 years. This might not be global warming, but if we have more and more data, just for 100 years, 200 years, we can see more about that. But currently, we only have for 40 years for sea surface temperature data and North America temperature data. Yes. Yes. Of course. Yes, this one.
What variables and how you defining the different variables and you consider which are like what are the different types of variables here and why do you choose between these different things?
Okay. And we have our decision variable as a coefficient vector and a binary decision variable because if we hope to give sparsity, we need to introduce a linear constraint in mixed integer programming. So we have a binary decision variable as beta. If beta is 1, then the coefficient for W is 0. Oh, if this is 0, then this one is 0. If this one is 1, then the coefficient is between 0 and 1. This could be a kind of value interpretable. In that case, the motivation for mixed integer programming is solution quality because if we use a gradient method, it's very difficult to find the optimal solution in terms of this kind of optimization because L0 norm is empty hard. It's very possibly we can find optimal solution, but in most of the cases it's not. And with mixed integer programming, we have linear constraints. We have nonlinear objective function. Then sorry.
Easy to solve this.
Not easy because it's more computational costly, but the solution quality is better. Yeah.
So is there any option of using any other model if you don't want to?
Another model would be Bayesian variable selection. We can use multinomial assumption instead for L0 norm because here we represent L0 norm as the sum of a binary variable. We can also choose a multinomial assumption with a Bayesian framework for the estimation. We can find uncertainty for the coefficient vectors, but the question is that Bayesian inference cannot provide the exact solution for that case. Mixed integer programming is the best solution if we have a deterministic estimate. Weights?
Tune exactly, right? That's the best part of
Yes, of course. Currently, we use the window size as 1 week. You can adjust as 2 week or longer because for our data across the whole year, we have 42 weeks across 1 year, and it's possible to adjust according to your lead. Thank you so much.
any other questions? Cool, thank you very much.
Okay.